Hi, in this video I'm going to talk about the bagging and ensemble modeling. We'll first learn about the theory and motivation behind bagging, and then we'll move on to compare bagging model with decision tree and linear regression models. The decision tree is very related to bagging. Bagging is just an improvisation on decision tree. In the last couple of videos we learned about the drawbacks of decision tree, and we will address the drawbacks in bagging. Okay, so bagging is just combination of decision tree. Before we start, I've just given you just brief introduction of what bagging is all about. Okay, in the third part of the session, we'll just take an example and we'll solve using R. So that is also going to be interesting. We'll see how bagging is able to improve the model accuracy. The last part of the session would be on questions. I'll give you some questions to solve, and if you're able to solve, I encourage you to send it across to me, and then I'll review and get back to you. So let's get started. So we'll start with the theory. Well, we have seen in the last couple of videos on decision tree that a single decision tree doesn't perform well many times. The good thing about decision tree is that it is easy to interpret. It's easy to understand and explain to someone, but it underperforms. And the reason it underperforms is because it is just single tree that is being used. This can be improved. Well, this problem can well be addressed. How do we address this problem? By combining several decision tree. If you are using several decision tree to model the same data, we'll be able to achieve higher efficiency or better accuracy of model. So the way to go about doing is combine several decision trees for the same training set, which would perform better in the test data. So that's the idea behind bagging. Okay, so bagging is just a combination of several decision trees. So that we can say in a nutshell. And how is that happening? Well, when you combine multiple trees, it is going to reduce the variance of your outcome. Okay, so that is how it is able to improve on the prediction ability of the model. So we can take an example to understand how you can combine observation to reduce its variance. I've got 3 observations. Okay, and you can take n number of observations. The variance of each one of these observations is sigma square. Okay, we have got 3 observations, s1, s2 and s3, and the variance of each one of these observations is sigma square. Now when you take the average of it, s1, s2 and s3, the variance becomes sigma square divided by n, where n equal to 3 in this case. Okay, so it becomes sigma square by 3. That means the variance has come down, right? It has come down drastically by combining or by aggregating, right? So that's what we have learned from the basic statistics, that when you do the averaging, when you average observations, that reduces the variance. Now in modeling, and you might have heard about what is known as bias variance trade-off. We're concerned about the variance of the result. If you take different data set, you will probably get different predictive accuracy of the model, and the variance could be more sometimes. That is not a good thing. So if the variance is more, then you probably won't have a very good model that will give good accuracy. So the idea is to reduce the variance. So the same technique that we learned here can well be applied in the case of decision tree. Instead of a single decision tree, we can fit multiple decision tree and take the average of the outcome, and then use that as the final model or final model for the training data set. And that's what we call bagging, the technique of bagging. So this is important. We will call it as bootstrap aggregations. So you might have heard about what is bootstrapping. I'll give a very brief idea about what bootstrapping is. Bootstrapping is nothing but sampling from the same sample, taking subsamples repeatedly from the subsamples. Okay, so we have got a sample here, and we are taking smaller samples overlapping samples, because the same observation could be in different subsamples from this bigger sample. That's known as bootstrapping, taking a subset of the observation, repeated, or rather, the same observation can be in the subsample, so it is replaceable. The observations are replaceable, and taking several samples from this bigger sample randomly is known as bootstrapping. Okay, and that will help us fitting a number of decision tree, because when you have multiple samples, you can fit multiple decision tree, right? So that's the idea. So just keep it in mind what bootstrapping is. And here's an example. We have got a data set of salary and education. So target variable is salary. We're trying to predict the salary of an employee based on the number of years of education. Now we have got let's say 15 observations. So we can take let's say 10 observation at random. Okay, so we can 10 observation from 15 observation randomly, and remember the numbers, the observations can be in different samples, so they're not mutually exclusive, so to say. The observations can appear in multiple samples. So we just take first sample, we call it as T1, and it has got 10 observations randomly picked from this main sample, this one. And we've got second sample T2 in a similar way, and all these observations are replaceable, by the way, and the same observation can be in T1 and T2 and T3 as well. So, and then we took the third sample. Now what we'll do is that we'll fit a decision tree on T1 and a separate decision tree on T2 and another one on T3, and then we will have the the actual value and the predicted value for salary. Okay, the actual value of course is known to us here, and then we'll have predicted value. We'll have okay, let me show it to here. So we'll have predicted value for model sample 1, sample 2 and sample 3, right? We'll take the average of that and we'll call that as the final one. Okay, the averaging will give a better result. Okay, so the idea is same, except the fact that when you use it in practice, we'll use a different way of doing it. Okay, so it's just an explanation. It's not the way it actually is actually done. There's slight deviation from this one, and we'll see in the next slide how do we actually build. In reality, it's very difficult to take a sample, build a training set, and take do the average. So the way we do is take a bootstrap sample or use bootstrapping in order to repeatedly get multiple samples and fit our data. So it's entirely automated, and we will see how it is purely automated way of doing, and we'll use R to do that. So the idea here is to build separate prediction model for each training set. So I've taken 3 training sets in the previous slide, and you can take n number of training sets and fit a separate prediction model. It could be decision tree, it could be linear regression, it could be logistic regression, or any of these models. Mind it, we're not only talking about bagging on decision tree. We can do it for linear regression and logistic regression as well, and we'll then average the result. So this is the 2 step. First, you build a separate model for different training set, randomly selected from, randomly taken from the main training set, and then average the result. So you build the model F1x, F2x. These are the different models that you have fit to your data, and you have fit n models to your n subsamples. Then the final model will be just average of that. Okay, so that's why it is called aggregation, bootstrap aggregation, or in short, bagging. Now, it can well be used for classification. Now we learned how to do in a regression problem, but in classification the steps would be same, except the fact that instead of averaging, you take the majority vote. Okay, pretty similar to how you fit a decision tree. In classification, decision tree is different from regression decision tree, right? In classification decision tree, you take the majority vote instead of the averaging, right? So you take let's say we have got 3 decision tree, and we have got circles and then squares. Okay, so here the majority is, let's say, circle. Here the majority let's say is square, and here the majority is is circled, right? So for the same observation, we have got two circles and one square. Okay, so the final outcome will be taken as the majority one, which is the circle, right? So that's the difference. Okay, you take the majority count or majority vote instead of averaging in the case of classification. But the steps are same. You take random sample and then fill multiple separate models for the different training sets. In reality, it is very difficult to get different samples ready in hand. You'll only get one sample, one big sample, or one population data all the times. So what you do is that you take 2/3, and it's not a thumb rule though. You take 2/3 of the data every time and then aggregate the result depending on whether it's a regression problem or a classification problem. If it is a regression problem, then you go ahead with averaging it out, averaging the value, or if it is a classification problem, you just take the majority vote. And the above method can well be used for linear regression, logistic regression, and decision tree. However, decision tree is always preferred in this case, but there is there is no thumb rule as such. You can go and well ahead with linear regression and logistic regression as well, and see if you're by taking multiple samples and multiple models and aggregating them is actually improving on your model or not. The next thing, or the next important thing to know in bagging is how you do cross validation. Normally, if you're building a regression model or a decision tree, you separately do cross validation, right? Build a model on training data and then test your model or validate your model in test data, and you do cross validation in that way just to find out what is the test error, right? What is the test error? And that's what we are interested in, because that's what we need to minimize, right? So we can do that with out of bag error estimation, and you don't have to do it separately in bag. You can do it on just one go and build the model and then do the cross validation at the same time. So here is we have got sample data, and as I've said, 2/3 of the data is being taken for model building, and it could vary, right? It's random. It could be anywhere. This particular line could be anywhere, here. It could take, like, if you're taking n number of subsamples, so n number of times you would take 2/3 of the sample for model building. So every time you will have 1/3 of your sample as the out of bag or out sample, so to say. So given that you're always using a out sample data in your model, you already have a cross validation done even while you are building the model, right? And that's exactly what is going to be used to calculate the out of bag error or out sample error. So for each observation, there would be b/3 out of bag errors, right? Because each observation would have an out one of the section is left out, right? And that section you will have a out sample error, right? And you aggregate that, you take the average of the out of bag error, and that would be considered as the test error, right? And there is no need to do cross validation in this case. You'll get it in one go, and we'll see that when we use R, you'll get the error right away. Then variable importance. This is also important to know. Okay, another important feature of bagging. Now you know that in decision tree, when you are building a decision tree, the good thing about a decision tree is that you know which variables are very important. The ones that are at the top are very important, right? And as you go down in the tree, you will get lesser important variables, right? That's how you rank order important variables in your data or in your decision tree model. But in bagging, you cannot visualize this. You cannot have this tree in place because you are using multiple decision trees. You cannot visualize the way I have visualized this simple decision tree. So in that case, the easy or the advantage of decision tree is now lost. So we have compromised on the interpretability of decision tree just to get a better accuracy. So now there is a trade-off between accuracy and interpretability. Now we have compromised on interpretability because there is no tree as such now, but we have increased on the accuracy. That's what our the motivation, right? However, you can easily get the most important variable from your model. Okay, and how is that done? Well, for a regression problem, you use a matrix called RSS, and for classification problem, you have Gini. And these two metrics will be used to rank order the variables used in the bagging model. So once you are done with the bagging model, you can get the most important variables by ranking all the variables used in a model through one of these metrics. Whether it's a classification problem, then Gini would be used. If a regression problem, RSS would be used. Then let's take a case study to understand. So we learned the theory, and one thing to remember is that bagging is just a combination of so many decision trees. That's what you need to keep in mind. That's the only takeaway from the theoretical part. Now let's take an example to understand. We'll take the library ISLR because there is a dataset called car seats. I've used the dataset in the decision tree problem in my previous video. You can watch that video. The link to the video is there in the description section. And then I'm going to load the okay, let me show it to you. So I'm going to load the package random forest. Well, if it's not installed in your system, just go to packages and then install it first before loading it. And that's the package I'm going to use to build a bagging model. I'm going to take the dataset car seats. So let's see what's there in the data. We've got sales of the car seats, and there are several explanatory variables. There are 10 of them, 10 explanatory. That's the target variable. Sales is the target variable, and it's a continuous one, right? It's a continuous one that you can see. So it's a regression problem, right? It's a regression problem. So we'll try to predict sales with the help of other explanatory variables, okay? Income, advertising, population, and so on. There are 400 observations and 11 variables. Okay? One is target variable, rest 10 of them are the possible explanatory variable. So before we start with the bagging model, let's first build a decision tree model, because we need to compare whether a decision tree, whether a bagging model is actually improving on the decision tree or not. So we'll load the tree library. That's what we're going to use for building the decision tree. So we'll use the function tree, and dependent variable or target variable is cells, and will all the other explanatory variables, like 10 of them, right? And the data set we are using is car seat, and we have taken 200 observations. 50% of that, we have got 50, right? Total is 50, so total is 400. We are using 200 in the training data set to build the model, and rest for the test data set. And then once that is built, we are predicting using predict function. We are predicting the target variable in the test data, and then the next step would be to find out the root mean square error. How do we find that? We just subtract predict minus the actual target variable from the test data, right? So it's like predict minus actual, and you square them. Take the mean of it, take the mean, and you would get the test error rate, right? Test error, and that's the matrix through which you can compare two models, right? The one that is giving least test error is the best model, right? The test error that we are getting here is 4.7. I'm not going to show you the result from decision tree. You can always try it out yourself. The code is in front of you. All I'm interested in is what is the test error, and that is 4.7. So I need to see if the bagging model is actually improving on that or not. And when I'm visualizing the predicted values and the actual values, I'm seeing this data, and it seems to be not a very good fit. And let's see, because there seems to be higher variance. Let's see if there is an improvement on this or not with the bagging. So let's see if a bagging model is actually improving. We should have been in the previous slide. So first we are getting a training and test data using sample function. We're using 200 observations in the training data set, and in test the rest of the observations are there. So we'll fit a bagging model using the function random forest. The target variable cells, and we'll use all the variables in place. The data set is car seats, and we'll subset it for training data set only. And remember, we talked about knowing the importance of each one of these explanatory variables. To know the importance, you have to use what is known as importance equal to true. If you don't want that, you can simply remove this option. Otherwise, just keep it. Okay. Now, once you have run this model, we are seeing what is there in the result. Now, the result shows that the number of variables tried at each split is 3. So we haven't specified how many variables are to be used for split explicitly. It is using 3. Okay. And the number of trees it is taking, that means number of samples. So there are 500 random sample through bootstrapping has been used, and 500 decision trees have been used to do the prediction, and then it has been combined. All that has been automated within random forest function. Okay. So imagine if you do it manually, coming up with 500 random samples from the main sample and fitting 500 decision tree, and then using the aggregation is a daunting task. You just have to use a function which is already doing the entire thing. The mean square residual is 3.21. So what was the mean square error? Okay, so this is on test data, so we can compare. So let's see what is there in the test data. So this is on training data, right? Yeah. So we can't use training data test error, training data residual error for comparison purpose. Okay. So let's do a prediction. So we have built the model using bagging, using the function random forest, and then we'll use the same statistics which is there in the variable fit to do the prediction, and we'll use the test data, right? Test data is something that is exclusive to the training data, and then once we predict, we'll just plot the actual and the predicted value, and this is what you see. This is much better fit than what you have seen, right, previously. So this is not so good, right? But here you can see it is much better fit, and the variance has come down drastically. You can see it is smaller, right, compared to what we have seen previously. And if you take the test error rate, it is 2.6. So what was the test error rate? Previously it was 4.7. So it is 4.7, right? If I remember correctly, let's go back to the slide. It is 4.7. So the test error rate was 4.7. It has now come down to 2.69. So the model performance has improved drastically because of use of bagging or multiple decision tree to do the prediction. Once that is done, okay. So another thing I forgot to mention you is that you can actually use how many variables to be used. You remember in the previous slide we didn't use how many variables to be used at each split, and by default it took 3. So by using the keyword mtry, you can specify how many variables is to be used, and that could make a difference. You can always try with different numbers, and you would get different results, and the one that gives you the least test error is to be selected finally. Using the function importance, and in the bracket, and you use the variable in which you have the model statistics, and you will get the rank ordering of the variables. Okay. And how do you know which one is the best? One that is that is most important for your model or for your data is going to be selected by two matrices. Okay, one is a percentage of change in the mean square error and node impurity. So I'm going to explain you what is percentage of change in the mean square error. That means if you remove one of these variable, how is it going to affect the mean square error? So if you remove comp price from the model, it is going to increase the mean square error by 13.70. So it is very important variable because it is If you drop that variable, it is going to make the model worse. It is going to bring down the performance by a large quantity, which is 13.7, right? And then another important variable is price. If you drop this variable, the percentage increase in mean square error is 45%. That's a quite big number, so that's important variable. And self LOC is also important because that is also bringing down the mean square, bringing up the mean square error if you drop that variable. So you can actually plot with respect to the ranks, and it is going to give you, or you can actually interpret better. So this is how the variables have been ranked. The most important variable is this one, followed by price, advertising, comp price, and so on. Okay, so yeah, you can use one of these metrics to compare variables. Okay, and that's important because that's one of the lacuna that you have in bagging, that you cannot visualize the model, unlike in decision tree, where it is very easy to know which one of the variable is so important, the one that is at the top. So you use this particular matrix. Alright, now we saw how bagging can be used to improve on the model accuracy. Now this is an assignment, the two simple assignments for you. Assignment 1 is take a classification data, take a regression data in the example that I have shown you, take a binary target variable data, and then use decision tree and bagging to classify the way we have classified and compare the result. Okay, we have done it for regression. I encourage you to do it for classification. The steps would be same. Just build a decision tree, check the test error rate, and then use a bagging model and check the test error rate and compare the test error rate for both these models and see if bagging is improving on the prediction accuracy. The assignment 2 is use a linear regression model for bagging purpose. Instead of decision tree, go ahead with linear regression. Okay, and do it manually. Don't use any automated procedure. The way we have used random forest function, right? So fill multiple linear regression model and take average of them. When you do it manually, you probably can't take so many of them. Of course, you can write an automated function by yourself. Just take 10 or 20 models, or maybe 50 models, 50 random samples through bootstrapping, and then fit linear regression to each one of them and take or aggregate your result and see if it has improved your model or not. And you can use our email ID to let us know your assignments, and we will review and get back to you with the feedback. Thanks for watching this video. If you haven't subscribed to us, please subscribe, and also please visit the website which is there in the description section of this video. Thank you.